Okay, just 1 second. All right, so I hope the exam went okay. Sorry about that. Yeah, you can all hear me okay? Okay. How about now? I just want to make sure because I changed microphones. You folks can still hear me? I just changed microphones. Strange, I didn't hear anything. Okay, good. All right, so I was worried because I had to change microphones for my lecture. Just some reminders, and I just want to make sure everything's being recorded here. Okay, just some reminders. Start working on the multimeter lab. Homework 4 is due on Friday the 2nd. Homework 5 is due on the 7th. That's the chapter 27 homework, which actually goes quick. Just 1 second, I got to respond to a comment. Okay. So these are the new due dates. You won't see the new due dates listed on Canvas. I just haven't had a chance to update the Canvas. But on WebAssign, these are the due dates for the assignment. So go by the due dates on the assignment. Okay. All right. So what I want to do today is I'm going to continue our discussion from last week on capacitance. And I want to really talk about the energy stored in a capacitor, and I'm going to talk about dielectrics, and then have a couple of demos to do for you. So this is, just to recall, we defined capacitance as basically the absolute value of the charge on one of the plates of the capacitor divided by a potential difference between the plates of the capacitor. And the capacitor can have any shape. Now, the word capacitor has to do with two oppositely charged conductors. However, you can define capacitance for a single conductor, and I talked about that last week. In fact, you can define capacitance for multiple conductors, but we generally don't call them capacitors. But we really, when we use the term capacitor itself, we're really talking about something with two conductors that are oppositely charged. Okay. All right. So we also talked about how capacitors add in series and parallel. Okay. And we also did a couple of examples where we calculated the capacitance of a system based on this definition. Okay. And basically, that's what we went through last week. And so now I want to take it a step further, look at the energy stored in the capacitor, and then discuss what happens when you insert an insulator in between the plates of a capacitor. And really, I'm going to focus on a parallel plate capacitor. What I'm going to say regarding dielectrics applies to any kind of capacitor. Okay, so let me start by talking about what happens, at least from an energetics point of view, when you charge a capacitor. So imagine the first charge, dq, reaching one of the plates of the capacitor. The amount of work that's required to move that first charge is zero because there's no field. You're moving the charge in no field. But to move the second charge and the third charge and the fourth charge, etc., they're going to be moved into against the field. You're going to put them on the plates. You're going to put the charge on the plates. And they're going to be experiencing the field. So the battery has to do work to put the charge on the plates once that first DQ is placed on there. Okay. So the question is, how do we write an expression for the work done, the work that's required to place the charge onto the plates? And so we'll start with an expression for dW, the work done, which is basically going to be the energy that's stored in the capacitor. We talked about that. The work done by an external system is going to go into storing energy into the system. So dW is basically Q delta V, but our Q is infinitesimal. But each time you put a charge, a dQ on the capacitor, your delta V changes. And so what I should do is write my delta V in terms of Q and C. And so all I have to do now is integrate this equation from 0 to Q final. And I have the energy stored in the battery. I'm sorry, the energy stored in the capacitor. I'll integrate Q over C dQ from 0 to Q final. Let me call these primes because I'll make these dummy variables. And so that's the energy stored in the capacitor then is Q squared over 2C. I can rewrite this different ways because of this equation. I can rewrite this in the following manner too. No, I cannot hear you for some reason. And I had the sound turned all the way up. Not sure why. Hold on a second. Let me see it. I got my sound turned up all the way up. Let me check something. You guys can hear me okay though, right? Oh, I'm sorry. Yeah, I'm not sure why I cannot hear you. Just give me a second. Are you folks unmuted? Go ahead, Andrew, say something. I don't hear anything. Wow, that's strange. Okay, let me check my settings. Hold on, let me see if I can connect another speaker. Actually, I can't. I don't have enough USB. Oh, I know what I can do. Hold on a second. I have a Bluetooth speaker, so maybe I can try that. Give me a second. No, my new mic should be two-way. Oh, hold on. Go ahead and say something now.
Hello?
Okay, now I can hear you. There was a setting. I'm sorry, there was a wrong setting. I apologize. The speaker was set to some weird setting. I don't know what happened. Okay, so are we okay now? Can I continue, or did you have a question?
Can you hear us now?
Yes, I can hear you now.
Oh, okay.
I'm sorry. I don't know what something got changed. Okay, so let me continue. Or let me go back to what I was doing. I said what I was saying was that as you charge a capacitor, it takes no work to put the first DQ onto the plates because the battery is not doing any work against the field. But now once you put that first DQ on, now you have a field between the plates and the battery has to do work to add the next charges. And so we have to write an expression for the amount of work that's required to put the next DQ. And we got to keep doing this and sum over all the DWs because each time we add a DQ, this guy changes. The delta V does depend on the amount of charge on the plates. So as you put more charge on the plates, the battery has to do more work to put more charge on the plates. Okay. And so I rewrote my delta V as Q over C using this definition. And then I integrated the equation. I integrated this equation basically from some initial value 0 to some final value Q. And I changed the variables to primes as dummy variables. And then I integrated it. Okay. So, by the way, and I've had this question. Let me answer this question. I'm sorry, I keep breaking up the lecture. But if you had trouble submitting the exam, email it. Okay. Now, it might take longer to grade the emailed exam, but at least I'll have it. And I'll have a timestamp as to when it was mailed, okay? I'm hoping that we stop having those issues. All right, let me go back to here. So when you integrate this, you get Q squared over 2C for the Q squared over 2C for the energy stored in the place of the capacitor. Using this definition, then we can rewrite U in two different ways. Are we clear on that? So there is energy stored in the plates of the capacitor. Now, one interesting question I can ask is this. Look, if I have a battery and I connect the battery to the capacitor and I charge it to Q, isn't it true that the work done by the battery is the total charge you added to the plates times delta V. But the amount of energy stored in the capacitor is this value, is half of that. Why is only half the energy go to the capacitor? Right, the battery delivers this, the battery does this much work, Q delta V, but the capacitor only stores half of that. Why is that?
Because there's two plates?
I'm sorry?
Is it because there's two plates?
No, it's not because of the two plates. It's really because of the wires. The wires have resistance. Right? The electron, as the electrons go through the wire, they're bouncing off the atoms in the wire. Half the energy ends up being lost by the resistance. And in fact, when we get to chapter 28, we can prove that. We can prove that quite easily. We can have a circuit and take into account the resistance of the circuit, and we can show that no matter what the resistance is, half the energy will be lost to the resistance of the circuit. Okay, which is interesting. But we'll see it. We'll see it when we get to chapter 28. The last thing we talk about in chapter 28 is what happens when you have a resistor and a capacitor in series. And is at that point we can examine this. Okay. All right. So here I have the derivation. So one thing I want to do is really focus on the parallel plate capacitor. And I actually want to look at the energy stored in the capacitor really from a more fundamental point of view, because I can write capacitance of a parallel plate capacitor because we know what it is. It's epsilon naught A over D, right? So C of the parallel plate capacitor is epsilon naught A over D. So I want to write the total energy in a very fundamental fashion. Okay? Just a second here. I'm going to write it as Q squared over 2C, which is going to be Q squared over twice this guy, and let me rearrange this a little bit, okay? Let's do this. But Q is basically the charge per unit area times the area. So I'm going to write it this way. So in this particular case, A means area. I know a lot of people had this question on the exam. Oops. Sorry. And of course, one of the A's cancel. So I'm going to get sigma squared over 2 epsilon naught times A times D. The electric field between the plates is sigma over epsilon naught. So let me replace the sigma with E times epsilon naught and let me go to the far board because I'm running out of space and I don't want to write too far down. And we get this expression that U is equal to 1/2 epsilon naught E squared AD. Now, what does the A times D represent for a parallel plate capacitor? All right, I have two plates. The area of the plates is A, and then D is the separation between the plates. I'm sorry? It's the volume. It's the volume in between the plates. So I can define U as 1/2 epsilon naught E squared. And we're going to call that the energy density. Okay, U is the energy per unit of volume. Of course, the total energy U is not just U times little u times volume. So this is a little u. That's a big U. Okay, the big U is not just U times the volume because E in most circumstances will vary throughout the volume. So one can write that big U is the integral of little u dV. I will not prove that here because you need the methods of Calc 3 to prove it, but you can show that in general, you should to calculate the energy stored, you have to integrate the energy density over the volume. And this is going to become important later on, this expression. Okay, so this is volume, and this is energy density. For the case where E varies, you have to set up an integral. Does that make sense? It turns out, I'm sorry, somebody had a comment?
Oh, I just said yes.
Okay, so it turns out that using this calculation can also allow you to calculate capacitance. There might be some cases where carrying out this integral to calculate U might be easier than using the definition of capacitance to calculate capacitance. Because in the end, for a capacitor, this is going to be Q squared over 2C. So once you evaluate this integral, you solve for C and you're done. Make sense? Okay. Oops, something happened. So, energy per unit volume is 1/2 epsilon naught E, and yeah, E is the magnitude of the electric field vector. And so, you can see electric fields, you can see that directly. Electric fields store energy, just like gravitational fields. So maybe I can show you a couple demonstration of how electric fields store energy. And I did this the other day with the light bulb, but I'll do it more dramatically today. Let me get my little demo. I left off the other day with this demo where I charged. Uh-oh, I lost the battery. Hold on a second. When my batteries fell out. It's always fun doing demos live. Okay, so I have the same circuit, but this time I put in a flash bulb. Okay, let me put it upside down. I put in a flash bulb. Okay, this is better when you're in class, but anyway, that's okay. So this is an old flash bulb that I used to use on cameras. Most of you folks probably have never seen these before. And so when you click the camera, this flash would go off. It would be really bright. Okay. Nowadays you have like a little flash on those phone cameras. Okay. So I'm going to charge. I've charged the capacitor, and last week I used it to make the light bulb go off. This week I'm going to make this thing flash. So you guys ready? So I'm going to dump all the energy into this flash bulb. Here we go. You see that? Are you seeing blue?
Yeah, it's pretty bright.
It's pretty bright. Yeah, so that's why I kept my face behind it, because otherwise I would be seeing blue for a while. Okay. And it gets real hot. I don't know if you can see. I mean, this thing's deformed. Okay, it gets really hot and the bulb gets deformed. Okay, so all the energy that was stored in this little guy was dumped into the bulb, and this bulb is hot. It's pretty hot. Another example. I had to videotape it. I had to have Tyler videotape it because I could not do it here. It's not a very safe demo. But I'm going to show you a video in a minute where we have two capacitors that are 10 microfarads. So this is a good example problem. We have two 10 microfarad capacitors, and we connect them in parallel. So here's my circuit. And we don't connect it to a battery. It's something more robust than a battery. So these are two 10 microfarad capacitors. So the equivalent circuit is this. Right, because capacitors in parallel add. So I have 20 microfarads. And then I charge, the power supply is 3,000 volts. 3,000. So how much energy is going to be stored when I charge that sucker up? It's going to be 1/2 times, I'm going to use 1/2 CV squared. One half times 20 microfarads times 3,000 squared. Okay, so let's calculate what that comes out to be. So 3,000 times 20 microfarads. It's about 90 joules. So we have these two big capacitors, and let me switch to the video so you can see the beginning of it. They're big, and they're dangerous. Let me switch to the YouTube that Tyler created for us. The video.
This demo.
So it won't be as loud as in the classroom, I will say that. So this is the two capacitors. Tyler has charged them up. And what he's going to do is short them. He'll turn off the power supply and he will short them. So here, I'm going to play the video.
We are currently charging up a very large capacitor.
Uh-oh, what's happening?
And we're going to use this stick, non-conductive.
No sound, sorry.
With
Hold on a second.
demo. We are
Now there's no sound in my video.
currently charging up.
Too many technical problems today. Okay. Try one more time.
This demo, we are currently charging up a very large capacitor, and we're going to use this stick, non-conductive, connected with a brass rod. And I'm going to connect those, and we're going to watch what happens. This demo.
Oops. So, when you're in class and that's done, that sound is very loud. And the flash is pretty bright too. One thing we probably could have done is turn the lights off to do that demo. And you would have seen it was very bright. So you get 90 joules you're dumping, and you see how fast the energy is dumped. My guess is let's maybe in microseconds the energy is dumped through that rod. That handle had to be a good insulator, because if it wasn't a good insulator, Tyler would be in trouble.
So basically all the energy is just lost as heat through resistance in the rod?
Yes. So when there are versions of that demo where all the energy is dumped into a really thin wire and the wire gets vaporized. I mean, we don't have we haven't really built something like that yet, but you can build one, and you could probably find them online. It's called the exploding wire demo. And they dump all that energy into, it's more energy than that. They have bigger capacitors, and they dump, 500 joules into a thin wire, and it sounds like a quarter stick of dynamite going off, and the wire's gone. It's completely vaporized. So let me, let's talk about electrical power. Okay. Let's say we dump that 90 joules in 10 microseconds. Okay. How much electrical power is that? 90 joules divided by 10 microseconds. Ten microseconds is 10 to the minus 5 seconds. How much power is that? 90 divided by 10 to the minus 5. Which is 9 megawatts. $9 million watts. That's the rate energy is being dissipated. If it takes 10 microseconds to dump that energy. And that wire has a very low resistance, so it takes very little time to dump that energy. Okay, and so, hence we get it's 9 megawatts. And again, that's an approximation now. It's a ballpark figure. I don't know exactly how much time it takes for the capacitor discharge. Okay, but that's an estimate. So we're looking at a lot of energy in a short period of time. And so when you're dumping that energy into the atmosphere, you have very rapid pressure changes in the atmosphere, and you hear that sound, and it's pretty loud. When you see that live, it's a pretty loud sound. And if you have a thin wire where you're dumping more energy in, it's a very loud sound. It sounds like a big explosion. So let me do a couple of demos. I'm sorry, not a couple of demos, examples, sorry. I've done 2 demos already. I want to look at, if this thing works. I want to look at the expression for the energy stored in a conducting sphere and highlight what that equation means. The equation for the energy density. I want to, given this expression, and I'll be more precise. It's the magnitude of the electric field, and this expression. I want to write an expression for the energy stored in a charged conducting sphere. And then I want to use it to derive its capacitance. And I derived the capacitance of a charged sphere last week. Now, when I use these equations, and I got to consider what my limits of the equation are. My limits of my integration are. My limits of the integration are based on the region of space over which this electric field is defined. I'll say it again. The integration limit is based on the region of space over which this electric field is defined. Right. For the parallel plate capacitor, it's easy, right? Because if I have a parallel plate capacitor, the electric field is defined between this volume, no problem. But a lot of folks have an issue when they do something like a sphere. So let me do a sphere, and I'll give you an example how to actually use the energy density to calculate the total energy stored, and then the capacitance. So if I have a sphere, a conducting sphere, and let's say it's charged to some total charge Q, some arbitrary number Q, okay? The electric field inside is 0. Okay, so E inside is 0. What's E outside the sphere?
KQ over R squared?
Yeah, E outside is KQ over R squared. And again, I'm not putting the vector here because I'm going to focus just on the magnitude, okay? Because I'm going to be integrating the magnitude of this field. Over what region of space is that electric field defined? Isn't it defined from the surface of this sphere all the way to infinity?
True.
So then my integration limits are going to go from the surface of the sphere all the way to infinity. So then to find U, it's going to be the integral from the surface of the sphere R, so I didn't draw that in, sorry, all the way to infinity, of 1/2 epsilon naught, and then this guy squared. Oops, a fourth. What is my element of volume? Well, since the field depends only on R, I can break up space into basically a bunch of spherical shells of surface area 4 pi r squared and thickness dr. The only reason why I can do this is because the electric field depends on R. Let me continue. Let me pull out some of the constants. Actually, there's a 4 pi in there too. So there's a 4 pi epsilon naught, a k squared over 2. And let's leave this intact because this 4 pi epsilon naught is 1 over k, okay? And then what am I going to integrate? Does that look okay? Did I do the
Nope.
did I do the algebra correct?
You missed the Q.
Oh yeah, that's important. Okay, that is a constant, so I'll put that outside. Okay, thank you. So I just got to integrate 1 over r squared. That's easy, right? Look, 4 pi epsilon naught times k squared. Isn't that just k? Because this is 1 over k, correct? So let me get rid of one of those k's. There's too many k's. And then what does this integral give me? And of course, this ends up being what? K q squared over 2r. It's positive. It better be a positive number. But this is equal to q squared over 2c. All the q's cancel, and I get k over r equals 1 over c. So c equals r over k. That's what we got last week. So I can actually use this. I can not only calculate the energy stored, of course I have to know the expression for E, right? But I can also use it to calculate the capacitance. And this is one of those systems I can either use a definition of capacitance to calculate C, or I can use this method to calculate C. There's some cases where only one or the other will work because the integration is too hard. Okay. So are we clear on that? All right. So I want to talk about, I want to go back to charge sharing again, because you get problems in this chapter on charge sharing. Suppose I have 2 capacitors. I have a 200 picofarad capacitor and an 800 picofarad capacitor. I think this is like almost the same problem I was asked of me as a student. I thought it was an interesting problem. Okay, and each one of them is charged to 2 kilovolts. Let's say I get first capacitor, which is 2,000 picofarads. I'm sorry, 200 picofarads. And the second one is 800 picofarads. And I charge them both. You charge them both to 2,000 volts. Okay? I get rid of the power supply. In the process of getting rid of the power supply, let's pretend no charge is lost, okay? We're in an idealized world. And what I do is I take the plates, and furthermore, let me be more specific here. Let's say this is positive, this is negative, this is positive, and this is negative. I take these 2 capacitors and I connect them to each other, like this. Okay, that's the problem. The question is, what happens? What happens? So let's go back before this. I want to calculate the charge on each capacitor. So the charge on each capacitor is going to be 200 picofarads times 2,000 volts. So if I do that in my calculator, 200 times 10 to the minus 12 times 2,000. This one's going to be 0.4 microcoulombs. And this one will be, if you do a calculation, 1.6 microcoulombs. The total charge is going to be 2 microcoulombs. Okay, so what I'm going to do is, I have these two capacitors. I know they're charged at 2,000 volts. I know how much charge is on each one. I'm going to connect them together. So tell me what happens. Anyone want to guess what happens? No guesses? And in fact, I forgot to write one more thing.
Do they equalize?
Yeah, so they're going to equalize, right? Until when?
Well, until the charges are equal.
But the capacitors are different. Remember the example? I'm sorry, go ahead.
Okay, so then the charge, like the ratio or charge density is equal?
The charge density.
I don't know.
So you're saying the fields on both plates are equal. I think that's what you're saying. Like,
Well, yeah, basically, because if the charge, yeah.
so let me ask this. When I charge these at 2,000 volts, isn't it true that one side will be at, can you see that green or not?
Yeah, it's all right.
Okay. Once this plays at 2,000 volts, this place is at 2,000 volts, and let's say this one is 0 volts. Okay? And now I connect a wire in between them. And I guess I'll use red again. Now I connect a wire in between them. How much charge will flow from this wire to this wire?
Well, wouldn't it be none because the positive plates are...
At the same potential.
Yeah.
Right, so no charge flows. And in fact, if charge would flow, it would flow until this potential is the same as that potential. Isn't that true?
That makes sense.
Yeah, that's the reason why I did the charge sharing example last week. Because that idea comes up over and over again. And then on this side, same thing. They're both at the same potential. So nothing happens, right? In this particular case, absolutely nothing happens. If I wanted to look at how much energy was stored in this capacitor beforehand, and how much energy stored in this capacitor beforehand, I'm going to get and then compare it to what I had afterwards, there's no change. In fact, if I want to look at the total energy stored, there's no change. That's because no work is being done on any of the charges here. So nothing happens here. So that's not an interesting problem. I mean, okay, it's an interesting problem, but the results are not interesting, right? Because this goes back to our charge sharing example we did the other day. But what if I do this? I'm gonna make life more complicated for you, right? What if I do this? I take the side that's at 0 volts, and I connect it to the side that's at 2,000 volts here, and then I do the same thing here. Now what happens?
Well, then it would short like in the video, right?
Well, that was a direct short. But yeah, I mean, let's pretend that the wires could take that change. I mean, yeah, you do have a short, but let's pretend that wire can take the change, because in this case they're connected to each other.
And that was a complete short, right? What's going to happen here? I have this at 0 volts, and this is at 2,000 volts.
Well, then they would equalize at this point, right?
Yeah, at some point they will equalize. And what that means is
charges
that.
will.
I'm sorry?
The charges will equalize on the plates.
Well, charge will flow until the potential on both ends are the same, right?
Yeah.
Okay, yeah, charge will flow. So when you mean, be careful when you say equalize, because they're not going to be equal in the end, but the potentials will be equal at the end.
Oh, yeah, because they have different capacitance.
Yeah, charge will flow until you reach equilibrium. That's true. But the charge will not be the same. The charge on this plate, I'm saying the charge on this capacitor will not be the same as the charge on this capacitor. Okay. Again, it's a charge sharing problem. So the charge will flow until delta V, oops, not that one, until the potential difference across the first capacitor is the same as the potential difference across the second capacitor. Or you can say Q1 final over C1 has to be equal to Q2 final over C2. Okay, well, I have one equation and two unknowns. Where do I go from there? Now what? Where am I going to get my second equation? Well, how do we do the charge sharing problem the other day?
Is it from the initial charge?
Yeah, how much, what's my initial charge? So what that means is this plate has negative 1.6 microcoulombs, and this plate has plus 0.4 microcoulombs. So the total charge I have is negative 1.2. This plate, when this plate is connected to this plate, initially I had plus 1.6 microcoulombs here and minus 0.4 microcoulombs. So the total charge in between these two conductors, this one and this one, is going to be 1.2 microcoulombs. So, and I always deal with the positive number. Q1 initial plus Q2 initial is 1.2 microcoulombs. And that's going to be equal to Q1 final plus Q2 final. So here's equation 1. Here's equation 2. And I just solve simultaneously. Okay, if I solve simultaneously, and I'm not going to go through the algebra. Okay, that'll be an exercise for you because you'll have homework problems like this. You get Q1 final is 1.2 or 5. Hold on a second. 0.24 microcoulombs. And Q2 final is 0.96 microcoulombs. Okay? And then I can figure out what V final is, right? I mean, I can then take this and put it here and then divide by divide by the 200 picofarads, and I'll get my final voltage. And if you actually do the math, this ends up being I thought I had the value. 1200 volts. The interesting question is, compare the energy I started with, compare the energy stored in the system when I started to the energy stored in the system afterwards. How much energy did I have initially?
That was the 2000 volts, right?
Yeah, they were both at 2000 volts. So I'm going to write it this way. What I started with initially for the system is going to be Q1 squared over 2C1 plus Q2 squared over 2C2. All right, you can do it that way. That's what I started with initially. And then your final is going to be Q1 final squared over 2C1 plus Q2 final squared over 2C2. And so all I got to do is take the final minus the initial. So let me write the expression. By the way, there's multiple ways to set this up, okay? And in the interest of time, I'm just going to punch and give you the final result. I get minus 1.28 times 10 to the minus 3 joules. So where did the energy go? Why did we lose energy?
Wait, so how do you know it's like for initial and final there, you add them together?
Well, I have two separate capacitors, each stored with energy. Shouldn't the total energy be the sum of the two?
Oh, okay, that makes sense.
Okay. Yeah, and you can also write this expression in terms of Q total squared over the total capacitance too. Right, I did it kind of the longhand way. There's other ways to do this. Okay, this is probably the longhand way, but that's okay. The energy is lost because charge is flowing through the wires. Okay. So this is an interesting problem. At least I think so. Okay. Okay, so, all right, so I know I'm going towards the end of time here. I think what I'm going to do, and you're free to leave, I'm just going to keep recording so you can see this part of the lecture. So if at 2:05, what time is it now? If you need, oh, it is 2:05. If you need to leave within the next 10 minutes, just don't worry about it. This is going to be recorded, and I'll put it on YouTube. But I do want to finish this. So I want to finish the chapter so I keep on track. And so I have a lot of time next week to basically do series parallel circuits with resistors. And, you know, probably talk about the exam. So I don't have any problem if you end up leaving, okay? All right, so what happens when we charge a capacitor to some potential difference, delta V? We disconnect the battery and then insert a dielectric in between the plates of the capacitor. It turns out, if you do an experiment, the capacitance will increase. fact, if you're able to measure the voltage will actually decrease between the plates. And for most materials, the voltage will decrease by some constant, which is a property of the material. And we're going to focus on those types of materials, okay? Because they're easy to work with. So as you see in the slide, maybe let me expand the slide. You insert, so that red thing is the slab you put in between the plates. When you insert that, the voltage between the plates, the potential difference between the plates decreases by a factor. That is not a letter K. Okay, there's too many K's in this class, but that's not a K. That's the Greek letter kappa. Okay, that letter is the Greek letter kappa. I know it looks like a K. Okay. All right. So what does this mean? Well, if V by experiment reduces by a factor kappa, where kappa is a number bigger than 1, and kappa equal 1 for a vacuum, and Q doesn't change, and you know that Q is C delta V, that has to mean the capacitance increases by that factor. It increases by the factor kappa. Okay. So for a parallel plate capacitor, when you insert an insulating slab, the capacitance increases by the factor kappa, and so C is kappa epsilon naught A over D. That kappa times epsilon, the kappa times epsilon, is now called the permittivity of the material. The kappa times epsilon is called the permittivity of the material. Okay. So I'm going to kind of demonstrate the fact that the capacitance increases. This is something you would do in a lab, but this is going to be tough for me to do. I'm going to give it a shot here. Okay. I'm actually going to be using 2 cameras to show this. So let me change views real quick because I got to open up. Okay. So just give me a second here. Oops. I'm actually using FaceTime to video things twice. Just give me a second. I guess that's as big as the window gets, sorry. Okay, so what I have is I have a capacitor. I have a capacitor here, and this is a capacitance meter. It measures capacitance. Oops, wrong setting. So right now it's measuring the capacitance of the system. That's not correct. Hold on a second. Okay, the battery's low. I'm kind of worried now. Okay. So I'm measuring the capacitance of the system. Let me decrease the plate separation a little bit. And then what I'm going to do is insert this material in between the plates. So this is going to be my dielectric. I'm going to insert it between the plates. And you'll see it increases. In fact, let me do this again, but I'm going to make the plates closer. I'll have it in between. You see it's 0.102. And I don't know if in your end it looks backwards. I can't, for some reason I can't reverse the numbers on FaceTime. So the numbers on the meter are backwards. I apologize. I can't reverse the numbers. So it says 0.105 or 0.101. If I remove this, it goes way down to that's 0.058. And I know the number's backwards. But at least you get to see that the capacitance decreases when I take it out. When I put the dielectric in, the capacitance increases. Okay, that illustrates to you the effect of the dielectric on the capacitor. Okay, so let me switch views. Okay, let me turn my meter off because the battery's almost dead. So, what do dielectrics do when you insert them in a capacitor? Sorry. One of the things that it does is it actually increases the value of the capacitance. It also increases the maximum operating voltage because the breakdown voltage tends to be higher. And the breakdown voltage for dielectric materials is listed in your textbook. I don't expect you to know those numbers. Okay. The dielectric also provides mechanical support for the electrodes. Those are some of the advantages of having a dielectric and a capacitor. So some examples of dielectrics uses paper. And I did show you the other day of a capacitor where the dielectric was just paper. You can have a variable capacitor where you have interwoven metal plates with an air gap in it. And if you remember, there's a textbook problem like that. Those are used in old radios. You have capacitors that are filled with oils. Those are high voltages, high voltage applications. Those go bad if they get too hot. You have massive explosions. Same thing with transformers. There's some nice videos online of exploding transformers and capacitors going bad. And then there's the electrolytic ones. Basically, you apply a voltage and the oxide layer is formed, and so the oxide layer is the dielectric. But you have to, the polarity is important on them. If you hook them up backwards, if you put a big enough voltage backwards, they'll pop. Okay, so you got to be careful with those. If you're using an AC power supply, it's not a problem because the current changes direction. So why is it that when you insert a dielectric in the material, that the capacitance increases and the voltage decreases? Well, it's because of the fact that you polarize the molecules in the dielectric. You actually get a separation of charge in the dielectric. You form dipoles in the dielectric when you apply an electric field across it. So here's an example now of a dielectric in an electric field. So I put a dielectric in between the plates of an electric field. Okay. Basically you get the electric field, you get the dipoles aligned in the direction of the electric field. The arrowhead is positive the tail of the dipole is negative. Well, if you have that kind of orientation for all those dipoles, that's going to create an electric field that's in the opposite direction. All right, those arrows represent the dipole orientation. They don't represent the field produced by them. They're going to produce a field in the opposite direction. It's going to want to cancel out the field due to the plates. As a result, the field between the plates decreases because of this induced field. So that purple is the induced field. And so the total field in between the plates is the field between the plates minus what's induced. So let's write some of this stuff on the board. So field between the plates the total field E, and again I'm working with the magnitude here, is going to be E between the plates, the E created by the two plates, minus the electric field that's induced because all those dipoles are oriented in that particular direction. And so this is going to be equal to sigma over epsilon naught minus sigma induced over epsilon naught. Sometimes the sigma induced is called sigma bound, and some folks will call it the bound charge because they're bound to the insulator. And we say that this is sigma over kappa epsilon naught, because if the potential is decreased, the potential difference between the plates is decreased by kappa, then the electric field has to be decreased by kappa. So we can write it in that form. And again, we'll call this sigma over epsilon without the naught, where epsilon is kappa epsilon naught. And just to be careful, kappa, I should write like that. Okay, that's typically how you write the Greek letter kappa, as opposed to writing it at the apex here. You move the slanted line up some. Okay. So we can actually solve this for sigma induced based on the way we've written this. I can solve it for this guy. Sigma induced over epsilon naught. If I move this to the other side of the equation, you can write it in this fashion. And if you get a common denominator, what you get is kappa minus 1 over kappa. Now, if you replace the dielectric with a metal, a conductor, then the electric field will end up going to 0. If I have a parallel plate capacitor and I slip in a conductor in between them, this whole thing becomes a conductor, and the field goes to 0. So what's kappa for a conductor? fact, what happens is when I put the conductor in between the plates, E plates equals E induced. These two are equal to each other. If E plates equal E induced, then sigma induced has to be equal to sigma. So this whole thing has to be 1. What should the value of kappa be so that this ratio is 1? I can look at it up here. For conductors, kappa is infinity. Okay? For conductors, kappa is infinity. For a vacuum, kappa is 1. So let me show you from a diagram, diagrammatically, what happens when you put a dielectric in an electric field. Here's a dielectric in an electric field, and what happens when you put it in the electric field, you're going to get a dipole created. So the second figure shows the dipole that's created. So you have a dipole field and an electric field. The last figure shows the sum of the two fields. Notice that the field lines inside the dielectric sphere, are less than those outside. The dielectric reduces the number of field lines that penetrate through the material. That's why epsilon is a measure of how the field lines will penetrate through the material. So if kappa is bigger, the field lines will not penetrate as much through the material. So for example, a conductor, the field lines don't penetrate at all through the material because the field inside a conductor is 0. So kappa is infinity. So I hope that illustrates that for you. For dielectric, it's somewhere in between. So, in the remaining time, I'm just going to do some examples of this, how to apply this idea. Suppose we charge a parallel plate capacitor. Oops. And let's calculate the energy stored in the capacitor. And then insert the dielectric when the battery is removed. And let's look at the energy stored. Okay, so here's a parallel plate capacitor. And I hook it up to a battery. U initial is going to be 1/2 C delta V squared. I'll write it that way. Then I insert a dielectric. So then I actually remove the battery from the circuit. I actually take the capacitor out of the circuit, and I assume that no charge is lost in the process. And I insert a dielectric. Whose value is kappa. What's the new energy stored? Well, then U final is going to be 1/2. So the capacitance increases by a factor of kappa, but the voltage decreases by a factor of kappa. So U final minus U initial is going to be this term minus that term. I have less energy. I have less energy stored. It's decreased. So why is that? Why is there less energy stored? Actually, the answer, and that's a hard question. The capacitor is actually the capacitor is actually sucking in the dielectric. It's actually doing work on the dielectric. Okay. So the energy goes into pulling in the dielectric. Okay. Let's do another example. Suppose we charge a parallel plate capacitor again. We remove the battery. And then we insert a dielectric so it takes up half the volume in between the plates. So I start with this. And I end up with this. What happens? It's not connected to the battery when I do this. Isn't it true that the charge is going to rearrange itself on this side and on this side? So that let me label this in terms of two sides, the left and the right. The charge Q is going to rearrange itself so that you have Q left on this side, minus Q left, plus Q left. And on this side, you're going to have plus Q right and minus Q right. And the sum of these two got to be equal to that, because charge ain't going to go anywhere. And that means that sigma left, at least the magnitude of sigma left, is not going to be equal to the magnitude of sigma right. But let me ask this. Let's look at the electrical potential in between the plates. And let me use a green marker. Let me draw an equal potential, because you know the field's uniform here, right? So let me draw an equal potential all the way across. What happens when you reach this surface? What happens here? You reach a boundary. The electric potential has to be continuous. So the potential here and the potential here have to be the same. So delta V left has to be equal to delta V right. Because otherwise you have an infinite field there. So that means if delta V left equal delta V right, that means Q left over C left equals Q right over C right. But I can figure out C left because that's going to be epsilon naught, half the area, divided by, kappa, epsilon over D. C right is going to be epsilon naught A over 2 D. So let me rewrite this. And C total, because if the potential difference here and here is the same, they're in parallel, okay? They're in parallel. So C total is going to be the sum of these two. And if you see kappa equals 1, I get epsilon A over D. Okay. Now what? So we've established that the fact we have actually two capacitors here that are in parallel. What else can we write about this? Well, you can see that C left is kappa C right. Okay. And we can find Q left because we can find Q left. Just 1 second. Let me check my math here. I think I have a mistake here. Hold on a second. Oh, we can say something about Q left and Q right and C total. I mean, in fact, C total and Q total can be written as delta V times epsilon naught A over 2D kappa plus 1. C times delta V. So we can also figure out, based on this information, we can actually solve for Q left, and we can solve for Q right. You can solve for sigma left, and you can solve for sigma right. And you can show that the electric field on the left is equal to the electric field on the right. Okay? You can show that the electric field on the left is equal to the electric field on the right. You can show that Q left is equal to, in the interest of time, I'm just going to write it down. Q total, kappa over kappa plus 1, and Q right is Q over 1 plus kappa. So you can show this based on this information, and this information. And I don't want to take the time out to do it because I'm just getting late for me. Okay? So we can show that this is the case. And if I have time, I'll make a video that shows all this. Okay? And then you can actually show that the electric field on the left equals the electric field on the right. This divided by the area gives me the charge density. This divided by the area gives me the charge density. But then you can show that the electric field on the left is equal to the electric field on the right. And if I have time, I'll make a video for that to show you all the details. Okay, because I don't want to take up too much time. Suppose I have a capacitor like this, and I insert a dielectric this way. Now, how do we treat these two? How do we treat this as compared to this? Here, what I did is I treated these as two capacitors that are in parallel that have half the volume. What do you think I'm going to do in this case? The electric field will be continuous here. Not the field, but the electric potential will be continuous across here. And it's okay to have a different potential here because the electric field is perpendicular to it. The total voltage drop is going to be this plus this. So then you say these are in series. If you have a system that looks like this, these two are in series, but this combination is in parallel to this one. That's how you treat them. And again, I don't want to go through all the arguments. Okay. Suppose we charge a parallel plate capacitor to Q naught. We remove the battery and you insert the dielectric. Okay. I want to calculate the force on the plates. So the battery is removed and we insert a dielectric. I want to calculate the energy stored in the capacitor and the force on the plates due to the field. Okay, so we need to write an expression for the energy stored. And I can do this question with the dielectric in place or not, but I just did it with the dielectric in place. So here's a capacitor. And I put in my dielectric. And its dielectric constant is kappa. And I'm going to write down the energy stored. Okay, I'm going to write down the energy stored based on what we have done so far. We established that for this guy, the energy density is 1/2 kappa epsilon naught E squared. That's the energy density. And I put a kappa there because of the dielectric. Since the electric field is uniform, then the total energy is going to be this times the volume here. I want to consider what happens if I lift the top plate up. I want to consider what happens if I lift the top plate up. So what I want to do is look at U when the separation is D, and then U at D plus dx. I want to look at that difference. There's a special term for this called the method of virtual work. So U at D plus dx is going to be 1/2 kappa epsilon naught E squared A D plus dx minus this term. And this is basically going to be du, the change in u when you move it through a distance dx. So what does this come out to be? du is 1/2 kappa epsilon naught E squared A dx. du dx is 1/2 kappa epsilon naught E squared A. What is du dx? It's minus the force due to the field. Because if you remember from Physics 205, F, the force due to a field is minus du dx. So the force due to the field minus dv. The force due to the field is the negative of this. So if I pull it up a little bit, the field's going to try to pull it down. So this is the force on the plates. The force on the plates is downward. The plates are attracted to each other. Okay? That's how we calculate the force. And in fact, if I take the force per unit area, the pressure, that's going to be 1/2 kappa epsilon naught E squared. Notice the relationship to the pressure and the energy density. You'll see electric fields are when you talk about fields, there's a nice relationship between pressure and energy density. Okay. All right. So I think I'm going to stop here, and I'll try to, if I have a chance, I'll make some videos. I'll try to finish that problem off because I didn't want to spend all the time here to discuss that capacitor problem in detail. Okay. All right. So I think actually one more thing I want to talk about application. I'm not going to apply Gauss's law. I'm going to skip this. The time. Let me just say some things about capacitor applications. They are used in radios, They are used in keyboards. They are used in random access random access memory. They are used in electronic stud finders, which I don't, I wish I had one in my hand, and defibrillator machines. Another application is in musical instruments. The theremin is another example where you use of an application of capacitance. Okay, so I've covered everything in the chapter. I'm not, there's one example in here. I only do it if there's time. I don't have time. But maybe I can give you the answer to this question and you can play around with it. Okay? All right, so I'll see you all next week. Have a good weekend.